Hi, I'm Gabrielle. I'm going to be doing homework 2 part B. So in homework 1 and homework 2 part A, we were doing a bar, right? And we discretized the bar. And from that, we were able to find different sections and the heat temperature, heat diffusing through those bars, right? What we found when we did a linear algebra with that is that we found that our R could not be greater than 1/2 or 0.5, right? So there was a lot of limitations to our thermal diffusivity, our delta T, and our delta X as well. Through that limitation, that R could not be greater than 0.5. So in this part A, we are looking at the Craig-Nicholson because Craig-Nicholson can help us do this answer and then have less limitations to our R, because R, using the Craig-Nicholson, we can have no limitations. The number can be anything. But through that, we're going to have to derive that equation for it. And we'll have to use matrix multiplication to get the answer for this. So what we originally had, so let's write this out. What we originally started with was Tj n plus 1 is equal to Tj n plus, and then I'm not going to write R, I'm going to write what R is currently, so it's going to be the thermal diffusivity, and then delta T over delta X squared. And then this is multiplied by our Tj plus 1 and minus 2Tj and plus Tj minus 1n. So from this, we are given that it is du over dt is equal to the thermal diffusivity du squared over dx squared. So to get an answer like this, what we have to do is we have to take an average of these here. And so I'm going to take this and rewrite it. So we need to take an average of that. And when we take an average of it, we are going to use n minus 1 with this. So we're going to do the next time step in here. And we are going to have 1/2. So this 1/2 here, I'm just going to kind of highlight that because that's there. So it's going to be Tj plus 1, n plus 1, minus 2Tj, n plus 1, plus Tj minus 1, n plus 1. So we are going to do now is on the left side of the equation, we're going to have n plus 1s, and then we're going to have n's. And then also we have that 1/2, we're going to put that in with our R equation here. So these are going to be our R's. So through that, we're also going to multiply out our R. And then we'll go from there. So it's going to be Tj n plus 1. Then it's going to be subtracting of R. And it's going to be Tj plus 1 n. And then after that, we are going to be doing, so then it's going to be plus 2r Tj n minus r Tj minus 1 n. And then this, we're going to do the right side of the equation now, where we have Tj n. Then we have is plus Tj, well, we have to have that R after there. So R Tj plus 1, then plus 1. No, sorry. These signs are messed up. So let me fix this real quick. Okay, so this side here, so if we're looking at these here, that is going to be flipped over negative. So that's correct. It just needs to have that n plus 1. This is going to be flipped over here. That's going to be a positive. That's correct. Just needs to have n plus 1 and n plus 1. Okay, so those are all correct. Just forgot that n plus 1. So now we have tj n, and we're going to have plus rtj plus 1 and minus 2r tjn plus tj1n. Oh, and we gotta have that r factor there. Plus rtj minus 1n. Okay, so now we want to combine like factors that we have. So we have this tj, and we have this tj here, and we have this tj here, and we have this tj here. So we're going to combine those like factors. So after that, we're going to have is, I'm going to put the negative tj, I'm going to put tj minus 1 first. And that's because I want to have these in kind of from smallest to biggest, because it's going to help us when we do that matrix multiplication, at least for me to kind of keep track of where we are, if that makes sense. So I'm going to switch this around a little bit. So it's tj minus 1 and plus 1. And then we're going to have plus 1 minus 1 plus 2r tj n plus 1. And then minus r tj n plus 1. Okay, tj plus 1 n plus 1. Okay. And then for the right side of this equation, so we are going to do is, again, I want to start with tj minus 1 because it's the smallest in the time step and the displacement step. So rtj minus 1 and then we're going to have plus 1 minus 2r tj n, and then we are going to have plus r tj plus 1 n. Okay, so from this we can solve this for the Crank-Nicolson by doing a matrix multiplication for this, right? So for the matrix multiplication, we are going to have, here is going to be our temperatures that we're going to be multiplying by. So our temperatures go from TL, so the left to the T right. So T right. And so it's going to be starting T right is 0, T1 is T1. And then this is going to be n plus 1. And then T2, n plus 1, and then T3, n plus 1, and so on and so forth, because we discretize the bar into 100 sections. We're going to be starting the 0 section as our first section, and our n section is the 99. That's still 100 sections, so our last section of the temperatures in between the two heating ends of the section is going to be the 98, right? So again, with the problem, we had the bar was at a steady state of 20 degrees Celsius. Then we added 50 on the left side and then 80 on the right side. So we know those two ends temperatures. We don't know the middle temperatures and how that the temperature propagates through the bar. So we need to know the middle, and this is kind of giving us the middle here. So n plus 1 here. So from that, we can come up with is our left side. So if I said T2 is, and we're going to be multiplying this by n plus 1, so we have to do the left side of the equation. So if I have T2, that means J is going to equal to 2. So this is 2, this is 1, and this is 3. Those are also going to help us with where they are on the like. So if you have the matrix, where they are going to be in the rows, not in the columns. The columns, we're doing the J's. So this is going to be, so if we're starting with J, that's going to be the second row is 2, because the J is equal to 2. But based off of what these numbers are, it's going to be 1 for the first one, second one for the third one, and so on and so forth. It's going to be the columns depending on what that t is. Does that make sense? So we're going to write this out here. And again, it's going to be wider. So it's going to be from 1 to 98, right? Just like this one's going to be it's going to be 98 by 98. This one here is 1 by 98. So that gives us our answer. So here, I'm just not going to draw it out to 98, but it is going to go to 98. So next thing that we got to do. So if this is TJ is 2, that means that this first column, so the first column here on the second row, it's going to be -r. Then we're going to stay on the same row, and then we'll go to the second position, and that's where our TJ is. But that's going to be equal to 2. And so 2 is going to be 1 plus R, 1 plus 2R. And then again, we're on the third position. So third position, still on the same second row because that's what our J is equal to. And that is going to be equal to -R. Okay, and again, it is big, so it's not a 3 column. Continuing. So let's say we change J. So we change J. That means we are going to change J to 3. That means we're going down the column, down the row. So we're on the row 2 because J was 2. Now we're going down to 3. So 3, this is going to be 2, and this is going to be 4. So we're shifting the column. We're shifting these numbers over by the columns, right? So we're doing column 3, column 2, column 3, column 4 on the third row. So that's going to be equal to R, 1 plus R. I mean, this is kind of sloppy, but you get the point, right? So what's happening is this is just shifting the line. It's like a staircase shifting down the line, right? So let's say it's going to shift. Also, what we know is that in the spaces where we're not having these 3, it's going to be 0. So 0 here, 0 here. So what happens when our TJ is equal to 1? So we have 1 here, this is 0, this is 2. What's going to happen is we have our 2R, then our negative, and then our 0, and then another 0. So with that 0, the TJ 0 is going to be our left, right? And so we're going to have to do a different derivation, like we're going to have to derive it a little bit for that. But before that, let's look at the product. So if we do this and we do a product of this, the second one is just going to be equal to R to, if we have it as 2, the first one is 1 plus 1, plus 1 plus R, 2R, and then T2 and plus 1 minus R, T3 and plus 1. Okay, so, and then that's just for the second one, third one. If we're doing the third one, it's just going to be shifting. All this stuff is just shifting. So, from this, now this is 3, 4, and plus 1. Okay, so some problems with this is that we are on the second time step. We're not at the first time step. We need to know the first time step. So we have to do some things different with this. And also, we don't know these factors. We need to use what we know. And what we know is we know the left and the right. We were given those, right? So let's think about this equation if we were doing, like I said, this 0 here made that a left. So let's do that pretty much. So let's derive this again. So this is going to be, if this is, it's going to be R, negative R, and so if it is at the 0 position, it's at the left, so TL. And it's not at a time step because it's at the left. We already know that. it's going to be continuous on all time steps, so we don't have to really say it's at time step number 1. So then we're going to have very similar. Nothing else is really going to change except for this is going to be 1 n plus 1 minus RT2 n plus 1 is equal to, on this side we have R, and then this is TL plus 1 minus 2R T1 and plus R is equal to 2 and okay. And so let's combine like factors. So 1 plus 2R Tj n plus 1 minus R 2 R T2 n plus 1. Then we have 2R TL plus 1 minus R T1 n plus R T2n. Okay, so we're using this, we're going to plug it in for the T0 value, because this is going from T0 to T99, right? So what is our T0 value? Well, what is our T1 really? Our T1 is going to have that left, right? So it's going to be TR TL plus 1 minus 2R T1 n plus R T2 n. So when we do this, we can actually flip the other ones, and we're going to solve it with that. So what's going to happen is these negatives will switch. These become negative because we are changing what side we're doing. We're changing that deriving side. So these will be like this. Okay, so from that, that's good. So then we're going to move down. So blah, blah, blah. Now to the last one, right? So the last one, if we have that, it's going to be, so if I did plus 1 minus 2R 98 n plus 1. This one is RT 97 n plus 1. That's a 97. And then we have this last one is going to be RT right. So now we have something to go based off, and now we have like the left and the right and these. So that's going to help us be able to solve this. So that is the end of part A. So part B, B3, so part B2. So we're going to take advantage of the sparsity resulting in the matrix. We're going to be using SciPy.linear algebra SP solve to solve for the temperature profiles of the initial conditions to find a steady state of that linear profile. And then we're going to numerically demonstrate the increasing values of R and the accuracy of the Crank-Nicholson results degrade but remain stable. Okay, so this is what we had before, this is what we had. So I'm going to copy this here because we're going to have it's the same discretion of the bar. So the bar is going to be pretty much the same as we're starting with that array. So let's just look at this real quick. I'm going to change this to profile because we want to have I want to have a separate array that captures all these values, all these temperatures at different time steps, but different one than the first example. These are all correct, it's both ends of the bars are different. You have an array in the middle. So let's do that. So the first thing that we want to do is we wanted to, from what I derived originally back on my iPad, we were looking at we want to look at the first matrix. And in that first matrix, we had negative R, and then we had R plus 2R, and then negative R again. And that went down the line, like in a vertical line. So we could do is np.stack, and then we do here like that. And then in between these, we're going to do np.full. Because in each of them, you know how we have those different rows in there. And we want to be able to do a 3 by 98. But I'll show you why we want to do a 3 by 98 instead of 100 later. So we have this here, and then we have negative r, right? And then from this, we want to do np dot full. We have n, and then we have the, it's going to be 1 plus 2 times r, okay? And then the last one, dot full, and then negative r, right? So let's look at this. So yeah, this is good. This is giving us different values. Oh, also, let's change our r value up here. I want the r value to change. So what we were constricted on originally in part A of this was that r could not be greater than 0.05. So let's do 2 to start out, because that is bigger, you know. So, okay, we have these. This is good. This is what we want. Okay, and this is going to equal AB, so like AB matrix. So let's keep that in there. And then the next thing that we want to do is we want to derive RB. RB is going to be equal to, so that is going to be equal to what we did on our product matrix. Our product matrix is when we had our R and then equal to that. So the first thing that we wanted to do is we had R times RT, right? RT, and we wanted to exclude the last two. The -2 excludes the it goes from the starting point and it goes back to. So it's going to cut out the last two, right? Which is that. And then we wanted to have a negative. And then 2. It's -1 plus 2 times R. Nope, this one is negative on the inside. Then we multiply it by t, right? And then we're going to exclude the first one and then the last one on that one. And then plus, and then this one we're going to have r times t. We're going to exclude the first two, right? Okay. So that is our B. So the next thing that we want to do after this is, so with B, we were talking about how we have our left and our right. So we need to do a plus or minus of this. So B is 0 is plus or minus T 0 is T0, and then B -1 should be plus minus T -1, okay? Okay, so then after this, what we need to do is we can solve. See if that works. Okay. So now we use our function that they gave us. Our function that they gave us was sp dot, it says it in here, so we're doing the SciPy linear algebra solve. SciPy dot linear algebra dot solve, okay. And then what do we want to solve? We wanted to solve so we need to solve this by something. This needs to, I know it's A, B, and B. This is a 1, 2, 1. And this is underscore banded. So okay, so SciPy, we don't want SciPy. It's sp.linearalgebra.solve underscore banded. And then our 2 points are from 1 to 1, and then we have our first matrix and then our product matrix, which is B, right? Okay, now, since we're here, look at this. It says shape of A, B, and B are not compatible. So, like I said, when I said that this first one is going to need to be not 100, but 80, 98. It's because this over here is excluding the first two and the last two. So to make these able to be compatible with each other, you need to subtract 2, right? So you do that, you do that, you do that. So now, so these are not great numbers. They're not what we want. So we have to multiply by r, because we did not multiply by r here. So this should fix it. R2, R there. There we go. So this is also a plus right here. So we have from 50 to 80 here, and it's propagating through this, right? Didn't get them all the immediate numbers in the middle because it's been one time step, so obviously it's not going to go through the entire bar yet. But you can see that it's starting to get there. So yeah, the equation, I just added that plus sign here, added these 2 there. And then we changed these 3 up top. So now, this is what is going in between, the temperatures that are coming in between of this. So we can do T. So these are the temperatures in the middle of the bar, right? So I am going to put this in this one up here at the top. So I'm going to delete this here. So this is just going to give us one time step. So we need to do kind of a for loop to give us multiple time steps like this, right? So to do this, we are going to do is our for loop. So for I in range, and let's start out with 100, and then let's tab these back. No, I didn't want to do that. Tab and tab. Okay, so now we tab those all back. We have this, we have that, so we have our profile, so we're going to have to do an amend. So what we did up here, so tProfile.append copy. So T underscore profile dot append or T copy, right? T dot copy? T dot copy. Okay. So that should copy it. So this is going to keep our different temperature profiles, right? So this should be good. Okay. So the next thing we're going to do is do our graph. So let's copy this up here. Let's make our graph down here. So our graph, we're changing this to profile because we have a different one. We're starting at 100, so I'll do 20 to start out with. Okay, and then let's try like this. Let's see. Okay, so we did 100 time steps. We see that we're not at steady state with the bar yet. So that's okay. Let's move to 1,000. Right? And I'm going to change this to 100. Oh, okay. To 100. To 100. Okay. Okay, so we're actually at steady state now. So we have a straight line, and we have lines with that, and we're at 1,000. So kind of like if we look at this in the main differences between what we did on part A and what we did on part B with Crank-Nicholson is this got steady state at 10,000 time steps. This got to steady state at 1,000. Those are completely different numbers. Those are wildly different. And that's because of our R value. So let's change that to 4. Let's change it to 5. Oh. 5. Okay, 5. So we have less steps, right? So that means it's going to actually take a less amount of time for this to get to steady state. So let's change that to 10 then. Okay, so we're at 10. It's changing even more. So I'm going to cut this down to 20, just because it's going so fast. Let's see if we can see anything else. Okay, so now we're seeing something else here. We see this little squiggle. Okay, so we have R at 10. Let's try R at 100. So R at 100, you see these squiggle lines are having some instability, but not crazy instability compared to what we did in part A when we had a high R value. So there is some discrepancies. There is some things to look at when you're using this Crank-Nicholson, because this isn't going to have a completely stable flat line. It's not going to have it's going to have some instability because of this. You know, once you having this really big R, it is going to make your time steps very sharp. You are going to get to a steady state quite faster than you are on the other ones if you have a lower R value. But you do have to watch out for if you go to an exceeding level of it. And we can look at that because of our R value. So our R value is, well, I know what it is. So it is just 1/2, for this R value, it's 1/2 times our thermal diffusivity times our T divided by our distance. So we can see that with our R getting bigger, our time distance is going to get bigger as well. And our step time is going to get smaller too. So it is going to cause some variability with this, you know. So you do have to watch out for it. Like, it will work in cases that are, you know, closer to singular decimals, but not into the hundreds. You will have some instability. Compared to our other one, it is less, it is still more stable than that one, because that one we had temperatures that would go up to the trillions and billions of temperature ranges. This one is still in our correct temperature range, but there is some instability with that you have to worry about. So that is the end of part 2B.